So the today talk is towards useful visual XAI methods for human AI collaboration. And we are living in the era of AGIs. With the competition in scaling large language models, big companies have been showing the sparks of AGIs, the system that are generally smarter than humans. However, the tendency to generate errors without warnings makes people not to believe in AI agents. This is also known as hallucination. So there are two types of hallucinations, the intrinsic and the extrinsic. So in the intrinsic here, we can easily check if it's the error or not. For example, in this captioning model, the model say a chest approach with a mirror on the top of it, but we don't see the mirror, so you can see that, oh, it's a mistake. However, with the extrinsic object hallucination, I mean the common hallucination, we couldn't check it because it just say a chest approach with a letters inside. So we couldn't check that, right? So it's much harder if the AI is hallucinating. As the hallucination could even lead to catastrophic consequences. In 2019, a man from Michigan was wrongly arrested due to an error of a recognition model. Therefore, end users could not trust in hallucinating AI agents. So in the path towards more general intelligence, Microsoft recently they pointed out the importance of AI model interpretability to first mitigate the consequences of hallucinations, second gain the trust from the society, and the last enable human AI working together. So to enable such collaboration, XAI methods should be more user-friendly and practically useful for downstream users. The most promising medium for communicating AI with humans is attribution maps, as you know. For example, they can have highlight the discriminative features to teach humans where to look when distinguishing butterflies, in telling a movie review is positive or negative, or debugging model behaviors. However, when working in a teams with humans, it failed to assist humans to achieve good performance. We tested on RedCam, EP, HMO perturbation, and SOD. Like this, so RedCam, EP, and SOD. So we challenge attribution maps in an AI-assisted decision-making setup where the heat maps are used to help users decide if the AI prediction is correct or not. To put attribution maps in context, we compare them with a simple prototype explanation method. First, from the query and the AI model, we get the top one predicted label on the input. Then we come to the training set for the predicted label. Finally, we retrieve and show the three training samples that have the highest similarity score with the input. And interestingly, we found this simple method is better than all tested attribution maps. And you can see here the three nearest neighbors. It helps contrast the predicted label, the lorikeet, and the B-eater, the ground truth. And somehow we can see the distinctive features to say they are different, to see that, oh, AI is wrong.
So just a short clarification here, Jiang. If you go to the method, right? So in the method, what you do is you try to search for the input query in the database, or do you search the input prediction to the similar ones? What do you kind of search when you kind of search for lorikeet?
Oh, so we just showed on the training set of lorikeet in the training set in the database.
Yeah, but what is the query? The query is the vector representation of this query image, or is it something else?
The query is a representation of the image, so we compare the code size similarity between the embeddings of the image and the training samples.
Mm-hmm. Got it. Thanks.
And the other works in the same vein coming after us also found attribution maps ineffective for downstream tasks in computer vision. For example, here in predicting human outcome model outcomes, in discovering bias, knowledge, and understanding model failures, and in debugging spurious correlations that model learned during training. We suppose the low utility of attribution maps is due to its lack of rigorous evaluation, because usually attribution maps are evaluated on proxy metrics such as localization. If the heat maps highlight very well on the face of the lion, so we see that, oh, this is good. However, we found the poor correlation between these metrics. Actually, we tested on 3 metrics versus actual downstream utility, but the correlation is very poor. So it doesn't say that if you have a good score in metrics, you will have a good effectiveness for humans. So humans can still make a lot of correct predictions when attribution maps localize badly, and users still make wrong decisions when attribution maps localize perfectly. So we think it could be exciting future research to invent an automatic evaluation metric that more accurately predict explanation utility. And from the experiments above, you can see one limitation of XAI, the current XAI methods, is the first thing is attribution maps are not using external information beyond the input to explain, right? And the second thing is the nearest neighbors we are using are not pointing to the model attention. So it's us humans for image level comparisons. For example, here we have a 3 pair-to-pair comparisons, and it's in image level, not in the feature level. So it's not fine-grained, and it's exactly not showing what the model is looking at to determine if they are not they are the same or not. So for humans, when comparing two objects, we leverage feature-to-feature comparisons or correspondences. For example, in face recognition, right? We need to compare face-to-face, eye-to-eye, or chin-to-chin, something like that. So this motivates us to introduce an explain then predict image classifier. That is, for model computes the similarity of the input with the training samples. We need to see if they belong to the same category or not. So here from the input, we have a set of training samples, and we compare them at patch level. So the most similar class from the patch level comparisons is our prediction on the input. Here is evening grosbeak. Here is an example of correspondence-based explanations. The AI thinks the input bird matches the below evening grosbeak in the yellow eyebrow stripe, the dusky neck, and the yellow feathers. So this is how our classifiers work. First, with a query image, we find 50 nearest samples from the entire training set, and then we re-rank them using patch-wise similarity. And last, we take the majority vote among the top 20 to make the final classification prediction. Here, evening grosbeak, and we have a 13 over 20 samples. So the our correspondence-based explanations, our XAI classifier, they can be viewed like a narrow ranking model because it has 2 ranking steps. First, we query to the training set or knowledge base to have the short list of 50 candidates. And then we perform patch-wise comparison because the patch-wise comparison is a very expensive. So we just do it on the small subset of training samples between the query and each of the candidates to re-rank them to see what images the query is most similar in the patch level. And finally, the most similar category is taken as a prediction on the input. So once we have such explanations, we put them into a human AI collaboration model. So in the first model, the AIs advise humans by giving the explanations. Then humans need to decide on the yes or no task to believe, to say yes or say no to the prediction from AI. And interestingly, on ImageNet, where users are familiar with many object categories, our explanations do not help but hurt human accuracy. The failure could relate to the KDE effect pointed out by Gaulle in 2023, because humans see the problems trivial when they could overestimate their own competence, which leads to improper reliance on AIs. On both classification, our explanations are useful, helping users obtain highest accuracy. In the human AI interaction setting 2, where AI labels high confidence images, leaving the less certain cases to humans. For example, on the right side, if AI is highly confident with the 95%, we will auto accept the predict label parachute. Otherwise, we forward the samples to humans as in model 1. So in human AI collaboration, we call this delegation, conditional delegation. And in this table, human AI is model 1 here. Human only is model 1, where human is the final decision makers. And AI only is when we let AIs to auto accept or reject the predictions upon a confidence threshold. The human AI teams is the model 2, where we let both humans and AIs make the predictions. So overall, we see that when they are working together on ImageNet, the team obtain the accuracy higher than AI alone or humans alone. So we call this is a complementary improvements. However, in CUP, the effect of collaboration is the least prominent. The improvement is marginal. So if you are interested, please see our paper for more insights on why our explanations help users. So yeah, so it's kind of everything. So it's pretty short. So if you want to go details, so please tell me so we can discuss more further. So for my final remarks, I would like to express my deepest gratitude to Muhammad Tesiri from TU Delft, Nguyen from Auburn University, and Giang Kim from KAIST. So I talked about the need for AI transparency in the XAI error and the failed promise of attribution maps, and how we can go beyond prototypes by explanations with correspondences. And lastly, how we can leverage the useful XAI tool for human AI team collaboration. And there are some points for discussion. So as I discussed about the explaining the AGIs, because the large language models, for example, this example, the model could explain itself, could explain its generation. However, it's sometimes all the time it's overconfident. So people argue that confidence calibration will completely solve the XAI for AGIs, and this is very hot topic nowadays. So I hope we can have some discussion on this. And another one is, I think that every proposed proxy metric, for example, the localization, or we have many other metrics in the XAI, for example, faithfulness or the reliability. So this should be coupled with a human downstream evaluation. So for example, in the next study, if you use a metric, you can reliably compare with the old, with the previous results to see if your method is actually useful in this setting or not. And the last one, the third one is the harnessing the correspondences in textual tabular data in information retrieval remains under explore. The next thing is the modality of explanations for effective human AI collaboration. I think this is interesting. So how can we communicate with humans via text, via audio, or via visual explanations? Is still, I think, open question in the era. And the last one is the effectiveness of explanations depends on how users, or often the lay users, perceive them. So in this sense, I think analogy-based explanations are promising. So analogy-based explanation actually is simplify the explanation to layman terms, so it can help more understanding of humans. So yeah, so that's pretty much everything of my presentation. So I'm open for the Q&As. And if it's too fast and you want to go into details of any slides, please don't hesitate to tell me so we can come back.
Thanks a lot. I think we will go back into some of your slides and then go into the details.
Yeah, sure.
Questions from others first.
Yeah, actually, yeah, I may start with one question. Yeah, because I think the correspondence, so I think you highlight more maybe yeah, correspondence in concept level, maybe like they have similar eyes or similar, say like colors in the body, similar, say like features, shapes or something. Yeah, actually I know some, yeah, debugging and the explainable AI in computer vision. I think it's called the concept activation vector. So how do you achieve your correspondence here? Do you also say like adopt, say, explicit concept vector, or you just do some annotation to the image, and then based on the annotation, you try to do some ranking for in a supervised setting? How do you achieve the correct bounced ranking?
So in the concept activation vectors, they try to align the human annotation, human representation with the model representation, right?
Yeah.
So they are kind of trying to define the concepts inside the model, but here we are doing exactly the completely different. So with we don't care about the concepts, but we care about the features. So for example, we have two images. So we find if in the eyes of the first bird, where is the most similar in the second bird, and we do that by solving the optimal transport algorithm. So for example, in the first bird, we represent by a vector, right, 7 by 7. And the second one, 7 by 7 again, and we do the optimal transport, and we see that which patch is the most similar to which patch, and we draw the correspondence. So
okay, so yeah, so I roughly understand. So you mean you just yeah, like cut the image into different patches, and then you use each patch for retrieval, see whether other, say, patches in some other image match this patch.
Exactly.
Right?
Exactly. So
then how do you provide the supervision signal? I'm a bit curious. How do you
Oh.
provide the supervision signal?
It's interesting question. It is very to the point. So here we are not using any training. So because we retrieve the explanations without any training. So this I do not show this slide, but we also tested on the classification benchmarks, and we see our classifiers have some improvement in accuracy, not just in explainability but accuracy. So from the appreciation model, right? So you check the features, and then you just do the comparisons. So actually we cut out the classification head, and we replace by a comparison head, like a retrieval, to see if this bird is similar to this bird or not, which bird this is the most similar to, and we decide the position. So no training here, we just use the prediction models. It's free.
Okay. Yeah, I think I roughly get your point. Yeah, thanks.
Yeah. I can go details. Yeah.
Yeah, so I think I want to kind of double click Gauler's point here, right? I was also thinking about how do you come up with a ranking. So if you do not have a supervised way to rank, so you would probably do all pairs comparisons, right? So you basically segment the initial query image into some segments. Firstly, I mean, that could be based on computer vision stuff, which I don't understand much, but I assume that there would be a principled way to doing that. And then you probably, from your candidate images that your KNN candidate images that you retrieve, you essentially do optimal transport based distance between them to find out maximal matching, right?
Right.
But in this case, what is interesting to me is that you want to match representative patches of the object instead of all patches, right? So for example, in this case, the query is some kind of bird. You would want to match the bird features or the bird patches of your query to the bird patches in the candidate images. So how do you figure out, or how do you zero into those patches that you want to compare against? So in this query, right, how would you choose the patches which are higher weightage than some of the background patches, let's say?
Yeah. Thank you for the question. So in computer vision, we slice the image by 7 by 7. So we know in advance the spatial information, so spatial locations of patch already beforehand. So in comparison, for example, if my features is a 7 by 7 and I compare with another 7 by 7, so I can map back to the original image to see which patch is most similar to which patch, right?
That is clear. But what I'm saying is that let's say that there is one patch which is the bottom left patch of this image, right? Which is kind of some background patch. You might have extremely high similarity of this background patch with another background patch in another image, right? And you might actually give high similarity because these patches match. So all I'm saying is that you have to have high patch similarity where the patches also mean or contribute a lot to the actual classifier, actual classification label. No.
Um. So
Am I clear, or do I make myself clear? I can repeat the question again.
yeah, I'm not sure. I'm not sure. Could you rephrase that?
Yes. So, for example, in this example which I see, right? If you make a 7 by 7 image, right?
Yeah.
The top right corner or the bottom left corner, the patches that you will have, those will be background patches, right? This would be background of the image, not the. It would be something gray, no?
Right, right.
Right. So now when you compare this patch against your candidate images, let's say that you will also have high similarity with another image where the backgrounds match. The image does not match, but the background matches, right? So the background matching is highly will give you a high score, but not necessarily the image patches matching. So do you take this into account, or how do you kind of think about this?
I see. Very interesting question. So actually, we have a lot of cases that the background match background in the beginning. So we couldn't filter out that. So what we do is first we do the cross correlation between two images. So we can somehow filter out the background. So
Okay.
every correspondences fall into the background, fall into the outside of the correspondence map. We throw them out and we just pick the 5 most strongest correspondences as explanations.
Okay. I was thinking that you could actually, reduce your patches to the localized object, for example, right? So you can actually localize the object using whatever localization algorithms, and then you can kind of patch this localized part so that, or anyways, right? So you do some filtering to kind of filter out non-relevant
Yeah,
patches.
we do need a filtering.
Yes, yes. I mean, this is very similar in information retrieval on documents, right? So you have to throw out most unimportant or reweight your query in some sense so that you match relevant portions, right? Otherwise, you would actually get not so meaningful results.
Yeah, exactly.
Other questions? I will come back with my questions, but I want to give other chances. Yes, Robin.
Yeah. Thanks for the call first. And I was wondering if in some classes you got two subclasses. Is there room for having more prototypes, such as maybe if females, not the same colors, are male birds? Maybe sometimes it could be interesting to have more prototypes and maybe use other kind of patches. I don't know. Is it handled yet, or do you manage this case?
Oh, thank you, Robin. So your question is, if the bird is, for example, male and female or juvenile, they look different, right? So how could we ensure to exactly classify that case?
Yeah, and also to select the image to show to the human. Do you only choose one image, or maybe you could choose to have maybe two or three images, because the class has subclasses such as juvenile, or maybe strange colors because of females do not look like male birds.
So I would like to answer the first question. So we are testing on ImageNet and cup. So in cup they don't have a much such variations, but also when because we have a two steps, right? The first we do that we retrieve by the KNN on image level. So somehow we are filtering. We just get the most similar images by image level already. So this is the first thing. And for the second question, so we show to humans the most similar images in patch-based comparisons.
Okay, that answers my question. Just I was not sure. I understood it first, but no, it's clear.
Yeah, thank you.
On that, I actually need a clarification, just that I understand the entire process correctly, right? So you basically take a vector representation of your query image, right? It would be the last layer of your um, representation learning layer, and then you search for the KNN objects, and then you kind of re-rank them using optimal transport based matching, and then you do some majority voting, right? So among the classes to kind of find out the final class.
Exactly.
All right, and then if the human is involved, you somehow do a little bit of calibration, in the sense that, well, if there are two classes which are 50-50 coming up, you basically show the human, say, choose among one of them.
So actually, for example, we do majority vote on the 20 images, 20 last images. So it's a type, for example, 10 classify 10 species one and 10 species two. So we randomly, in that case, we just randomly choose one of them, and we show to user one of them. Like in this case, it's like a random choice.
So one of the things which these deep models show, you mentioned about hallucination and others, is one of a property of these deep models is they're not very well calibrated. Meaning they might actually say that they're very confident, right? 98% confident that this is one image, but they're confidently wrong. So I think one of the risks in using the softmax values as calibration values is that you're not so robust, right? So have you thought about other well calibrated methods, or post hoc calibration methods as better methods instead of softmax scores?
So for clarification, we did not use softmax. So we just do the majority vote. For example, we have a 20 samples, and
because this is KNN classification. Okay.
Yeah, right. KNN classification.
All right. Okay, good. So KNN classifiers, I do not know how well calibrated the majority thing is, but I think this would be better than softmax scores, actually. Yeah, that answers my questions. Yeah, that's good. One follow-up question, maybe, because I mean we are interested very much in text, or we love images, but we just don't have the capability about images, right? We have more capability in information retrieval and text. Do you see how a similar approach can be used for language tasks or retrieval tasks?
So I believe there's someone using optimal transport for image and text alignment, and also text and text alignment. So for information retrieval, I think we can also use the same approach like how we did. But I'm not very extensive on the literature in the textual information retrieval, so I'm not sure about that.
Any literature that you might know of KNN classification for the language tasks?
Honestly, no, I don't have.
Okay. Good. So any other questions?
Yeah, actually, I have one. Yeah, because based on your, say, correspondence, the stuff, actually, when I think about it, it's more like, say, actually, it makes me think about, say, the transformer, because the transformer, it's just as a, cross attention. So actually, I'm thinking like maybe in your method, it's more like for one image, you just split it into patches, and then for another image, you split into patch, and then you just try to match the patches. So it's a bit of like, say, you conduct a more, say, fine-grained way or match the elements of two images, right?
Yeah, so yeah, it's definitely relevant to transformer, but I don't think transformer is as explainable than this method, because this is explicit. The patch-to-patch comparisons is a very explicit, right?
Yeah, so in the transformers, what happens is that your attention maps are over extracted features, and the extracted features themselves might be non-interpretable. I think that's your point, right? So
Right.
Correspondence or the alignment is on the input space, which is slightly more understandable.
Right, exactly.
Okay, thanks.
Final call for questions. If there are no final call for questions, then no calls. I see no hands.
For the question from Gale, actually, I think that our model is more robust in OOD detections. In OOD settings, for example, here, if the wish transformer, we all know that it may fail in the OOD settings if it sees some adversarial attacks, or it sees some strange objects in the natural life. But our correspondences is consistently improve the ImageNet, the ResNet accuracy on robustness benchmarks. For example, ImageNet R-Sketch, the ImageNet is adversarial network, adversarial attacks, and even on CUP with it improved over KNN on in domain. So it just reduce a little bit, it should degrade a little bit of performance. So it's another advantage of using this rather than transformer, which could be easily, overfitting to the training set, to the distribution.
Okay, thanks.
Thanks a lot for this extremely nice talk. I definitely learned a new approach, and maybe in our survey, when we do our revision, we will probably cite you at least for one of the nicer applications of how can you actually use information retrieval, at least this re-ranking based on optimal transport theory, right? To think about explainable AI. We still are lacking one full section on retrieving multimedia, retrieving images and vision. That's purely because of lack of our expertise. But whenever we expand this, rest assured that you will find a mention. Thanks a lot for reaching out. And if you want to have a separate discussion one-to-one on other things, right, feel free to reach out. I'm always available to give you some time.
Yeah, thank you. I appreciate that.
All right, then with that, let's conclude this talk. Thanks a lot again, and catch you guys next time, whenever.
Yeah, thank you.
Bye.
Yeah, have a good one.
Bye.
Yeah, bye.
Thank you. Bye.